Just one short announcement. So Professor Florian Marquardt is already here. I mean, not right now here, but arrived yesterday evening. So his lecture starts tomorrow, but you are, of course, welcome to bother him with questions starting from today. I mean, he doesn't like hear it, but yeah, please bother him with questions. Perfect. Okay, so we see your slides, which is great. And today chair is Patrick Humbeli, so I think it's time.
So hi everyone. It's actually a real pleasure to have Lei Wang here with us. He joins us from Beijing, from the Chinese Academy of Science. And I think if you're in this realm of quantum sciences and machine learning, he's really someone to keep in mind. He's all over the place in this field. He does face detection with machine learning. He's into machine learning with tensor networks, in neural network quantum states. He's part of the YAO team, that's a Julia package for quantum circuit simulations. So he's really a big name in this field, and it's a real pleasure to have you here with the title, 2 Lessons from Deep Learning.
Okay, so thanks a lot for those kind words. Also, thanks for the kind invitation. So hello from Beijing. In the following 2 hours, I'd like to share with you 2 lessons I learned in the past few years from deep learning. So those are the, I think, useful or I think cool things that is going to be quite amazing to you. I hope so. When you use that for your research. So those 2 things are differentiable programming and representation learning. So I'm going to explain them. So by the way, through the talk, you are going to see that from this lens, you are going to see different learnable architectures like a graphic model, or in other words, a neural network and a tensor network and a quantum circuit. They actually share the same kind of framework. So I'm trying to provide a unified kind of scheme to look at those architectures. So first of all, differentiable programming. So this is actually a rebranding of certain existing techniques, just like deep learning. The word itself is also a rebranding of existing techniques from more than 30 years ago. So nevertheless, it emphasizes a fact that machine learning is doing something slightly different from the conventional computing. So basically, in the traditional way of programming, we write a piece of computer program and give it certain input. So it runs for a while to give us an output. But usually in machine learning, what we had was an existing data set where we know inputs and output, but we do not know how to connect those inputs and outputs in a more general setting. So we just give those training data to a computer, and the outcome of this calculation or the computation is going to spit out a piece of computer program. For example, a trained neural network is actually a computer program. And the hope is that those pieces of computer program is going to generalize well to unseen data to connect those input and outputs in a general setting. So this is the aspect that the word differentiable programming tries to emphasize. Andrew Kapasi, who is a director of AI at Tesla, he wrote those quite influential blog poster where he drew a circle that is so-called program space. That's all possible computer programs. And this tiny red dot is the program that human can write with limited time and limited intelligence. But Andrew tries to advocate a different idea where we specify certain search space and perform gradient descent search in such a space to find out useful computer program. So this is a differentiable programming. He called that software 2.0. So, and he listed many kind of advantages of software 2.0 compared to the traditional ones. You see, it's better than human, like we already saw for many of the real world machine learning applications. But how is those things connected to scientific applications, in particular quantum chemistry, quantum physics? So let me show you this demo. So I call this inverse Schrödinger problem. So we all remember the ordinary Schrödinger's problem. So from our quantum mechanics education. So basically someone gave us, let's say, one-dimensional potential. By solving this Schrödinger equation, we got ground state and excited state. We got all the physical properties. The question of inverse Schrödinger problem is that if I give you a ground state density, how to design the potential, this V of X thing, such that the ground state in the potential match the one of the given density. So this is the inverse problem in terms of the Schrödinger equation. And there are actually many different ways of solving that. So we can actually think for a moment, how can we solve such a thing, right? And actually differential programming provide a very direct, straightforward way of solving that. So I prepared a Google a notebook in Colab to demonstrate that. So we can actually have a very brief look at it. So by the way, this is using JAX that we are going to learn also from a tutorial of this school. So just like an ordinary machine learning kind of a problem, we set up, for example, a loss function. So in that case, the loss function has to be the difference between the given density and the solution we got from this forward Schrödinger equation solver. And once we have the objective function, we need to find a way to compute the gradient of the loss function with respect to the potential, because that's the object we want to kind of optimize. Then we put those gradient information into an optimizer. In this case, it's just a from SciPy optimizer. You see, after a while, for that quite strange looking target density, the program suggests that you should have such a potential, so in the yellow color, such that the ground state density more or less match the target density. So that's it. So it's a quite short demo, but you see, it's actually quite straightforward. So now the question is, what's actually under the hood, right? Because you see, what we did essentially was to set up a way to solve this forward problem. And magically, or let's say automatically, JAX, or those machine learning library, computes the gradient of the objective function with respect to certain parameters that I want to optimize. Then that's it. But what is the actual technique and the hood? This is what I'm going to share with you in the next hour. So to appreciate, I would say, the magic of this technique, we can think over for this question for a moment. So what is deep learning doing? So typically people is going to show you such a program, such a diagram where there is a very deep neural network, so which does classification and so on. But what does training such a deep neural network really mean? From a computation perspective, I'd like to view that as this sentence. So deep learning actually composes many pieces of differentiable components into a piece of computer program. So in this example, this computer program happens to be a neural network, but in general, it does not have to be a neural network. Then people just compute the gradient of the output of this computer program with respect to its input and optimize the behavior of this computer program so it achieves the requirement. So this is on a rather high level and abstract way of introducing deep learning. But I think this captures some of the essence because we can, for now, abstract away all those neurons and connections and so on. So behind this program, what's going on is actually something called computation graph. So computation graph is a way to express dependence of your data and variables in that piece of computer program. So behind that very colorful and complicated feed-forward neural network is such kind of a computation graph. So I call this a comp graph because it looks like a comp. So basically here each node, each circle indicates your data or parameters in the program. And the arrows, they indicate the dependence of your parameters. So running the computer program means you just follow all those arrows from input to the output. And now we'd like to get the gradient of the loss function with respect to the parameters and inputs, because we need this information to tune the behavior of such a computer program. And for the convenience, let's define something called a joint. So a joint means the gradient of the output with respect to the parameters, intermediate or the input parameters. That's it. So then by definition, in the end, the adjoint of my loss function is 1. Now I'm assuming I have a scalar valued loss function. So then the goal is quite clear. We need to kind of pull this R adjoint equals to 1 kind of information all the way back through that computation graph until we reach all those nodes that we are interested in is a joint or the gradient. And locally, we can pull those information back by multiplying this adjoint to a Jacobian calculated for that particular step. But this is quite a local calculation. So this is nothing but backpropagation algorithms for this particular graph. And it can be more general than that for an kind of almost arbitrary kind of a directed acyclic graph that is that includes loops and conditionals and so on, or kind of branches in your program. So you just need to think locally. So in the backpropagation procedure, each node tries to collect adjoint information from its child node, compute its own adjoint locally, and tries to send this information back to its parents. So if each node just follow the same rule, and if you assemble a large number of nodes into a computer graph, you can automatically carry out such a calculation. So this is called automatic differentiation. So calculating gradient of a computer program in this way has certain advantages compared to different ways. For example, compared to numerical finite difference. So numerical finite difference means you just run the program for a few times, each time with the perturbated parameters, then you do finite difference for its gradient. So automatic differentiation, like I showed you in a moment, it is accurate to the machine position. And it's also more efficient because you see, I just run the program forward and backward for twice instead of running it for many times to get the finite difference gradient. Actually, there is a theoretical guarantee. So if you compute the gradient of a computer program in that way, so the computational complexity is actually the same as function evaluation. And moreover, because the gradient of a computer program is a computation graph, so you can apply this idea iteratively to automatically compute the high order gradient of a piece of computer program. For example, you can change this to get arbitrarily high order gradient of a, for example, tangent function in this example. So there were actually many interesting applications of this technique to science. For example, people use that to compute the force, to control quantum system, and so on. But with the rapid development of the tool and the kind of spreading of this idea that simulation, or let's say computer program itself, is actually differentiable and learnable, people actually now try to apply this technique to more and more complex computer programs. For example, here, the authors was actually trying to differentiate through a long chain of Langevin dynamic simulation. So this is a stochastic simulation trying to backpropagate the difference in the structure of certain protein with respect to certain potential of those atoms, trying to learn the right potential to fold that piece of protein. So in the second example, what was shown here is a so-called Cone-Shen self-consistency calculation in a density functional theory calculation. Again, this is a long chain of calculation. And again, the authors here try to backpropagate the error signal related to the energy and the density distribution all the way through the calculation to tune the so-called exchange correlation functionals in the calculation. So again, this is a way to learn the exchange correlation potential. But through these two examples, you see that what was differentiated here was not simply a kind of a mathematical function. It's actually a simulation, right? So differentiable programming, in this sense, nicely combine a neural network model and an existing computer simulation code and make the whole thing differentiable. So you actually enjoy advantages from different worlds, because this kind of computer program is adaptive. Also, it incorporates the physical knowledge because it's already a Langevin simulation, or it's already a density functional theory, right? It's not a kind of a quite naive or quite a simple-minded neural network. It incorporates the existing theoretical framework. So another example turns out to be my favorite. Is related to the coil design in fusion reactors. So again, here the task is trying to design those coils so it can confine extremely high temperature plasmas. So you see, it can be rather complicated because this is an extreme condition and there are lots of physical and engineering constraints. But nevertheless, in the design, you can just view the cost function with respect to the coil parameters as kind of a computation graph. So in this example, there is actually no neural network. So each step is a ordinary scientific calculation. You do Fourier transform or inverse Fourier transform, you do integration and so on. But nevertheless, you can treat this as an ordinary computation graph and backpropagate all the way to the coil parameters, so you have a balanced design. So those are kind of quite recent examples where people apply differential programming, the technique, to scientific applications. And in the next like 15 minutes, I'm going to explain to you the techniques that was used. Because sometimes when you try to differentiate into a piece of computer program, you might need to have a bit of deep understanding than just use that technique as a black magic box. Okay, sometimes you need to know a bit of some kind of important, let's say, jargon. But what I'm going to see the topics you can all find in this automatic differentiation cookbook from Jack's documentation. Okay, the first, I think one of the most important notion when we talk about automatic differentiation is the fact that there can be so-called different modes of automatic differentiation. For example, there can be reverse or forward modes of automatic differentiation. So what are they? Again, let's think about one-dimensional computation graph. So then this is really a one-dimensional chain, right? So basically, theta is my input parameter. Theta gives me x1, x1 gives me x2, all the way to the loss function. So it's probably the simplest computation graph. And when you expand the gradient into a multiplication of all the individual Jacobians, this is nothing but chain rule. But even in this case, there's something interesting happening. So imagine how should we compute the outcome given this long chain of multiplication. So notice that here, I'm assuming my loss function in the end is a scalar value, where the parameters, they are high-dimensional tensor or vectors, and the intermediate results, again, they can be high-dimensional. Then that means efficient way to compute the outcome is actually to multiply those matrices from left to the right, because here this is essentially a vector, a row vector. You multiply a vector to the Jacobian, then to another Jacobian, right? So this is called reverse mode automatic differentiation. So in the sense that the way you compute the gradient backtrace the computation graph, right? You start from the end all the way to the input. So this can be somewhat inconvenient because you might need to store some intermediate result. But nevertheless, this is very efficient if your output is a low-dimensional object and the input is a high-dimensional input. So this reverse mode automatic differentiation, when you apply this to a neural network, this is called backpropagation. Not surprisingly, if we multiply those Jacobian from right to the left, we get the same answer, of course. However, the computation complexity is different because we start from the fat end. Those are all the matrices until in the end, you multiply matrix to a vector. So this is less efficient. However, it's convenient because you are computing the gradient in the same time as you're running the program. So this is called forward mode automatic differentiation. So, but these two are just the extreme case. Imagine you can, for example, start from the middle, or for more complex graph, you can kind of group different steps and so on. So actually for a general computation graph, what's the optimal way in terms of the computation time and memory to get a gradient? In general, it's an NP-hard problem. So this is the first basic notions of automatic differentiation. So another important fact related to automatic differentiation is the word granularity. So it means that, for example, even in this case, so suppose you can group a few steps into one step. You can call this step as an elementary step, as long as you know how to compute its Jacobian, or in other words, it's the action of this Jacobian to a vector. So in this way, you can actively control the granularity of your automatic differentiation systems. You can differentiate all the way into mathematical intrinsics plus modification and so on. Or you can group many steps together and write so-called customized primitives. So this very often is advised because imagine you had certain linear algebra calculations, for example, matrix multiplication or matrix diagonalization written in ancient Fortran blocks or Laplace code, where you do not want to differentiate into. So you can wrap them up and provide another rule for computing is a Jacobian vector or vector Jacobian product. Why this way you glue together? Yeah, please.
Can we representation? Yes.
Please.
Hi, I wanted to ask, because I didn't quite understand if you compared it, calculated in the reverse mode versus forward mode, why is there a difference? I mean, at what point in network would you do that? Aren't all these vectors or matrices set? Or do you still update them as you go through? So
the result certainly will be the same. They are different in terms of the computation flops. The amount of calculation was different. So because in the reverse mode, you multiply, because notice that this is a vector.
Yeah, I understand why it's more like why the reverse mode is more efficient, but you said in some case the forward mode is better. Why is the forward mode better? And
oh, okay. You mean why in what case forward mode can be better, right? Is that the question? Okay? So imagine for certain applications that actually theta is a low dimensional parameter. For example, theta is one number, while this loss function L is a vector or tensor. So in this case, this becomes the small end. This is the bigger end. In that case, you need to multiply from right to the left. Yeah.
Okay. So we just look at like which end is smaller and then start.
Yeah, that's a kind of rule of thumb. But in practice, suppose this is L and theta, they are tensors with the equal dimension. Suppose in that case, forward mode is still advised because it will use less memory. Mm-hmm.
Oh, okay. Because you evaluate at the same time you evaluate the function.
You do not need to store intermediate result. Yeah.
I see. Thank you very much.
Yeah. Actually, we are going to see some of the examples of this. So typically we use for reverse mode, but in certain cases, high order cases and certain applications, we are going to see that forward mode can be useful. Yeah. Very, very good. I was talking about control those granularity by defining primitives. So another possible application is actually to think of hybrid classical and quantum computation graph, because nowadays people talk about hybrid classical quantum algorithms where for certain calculation happens on CPU, certain of the things on a GPU, also the QPU, so on actual quantum device. So actually you glue those primitives in the same way as you glue external libraries like blocks and Laplace. Okay, so AutoGrad is a pure NumPy library for automatic differentiation. So you see that just by spotting around 200 primitives, it covers most of the NumPy. So you see many of those things, they're just one line. And moreover, actually those control flows like loop, condition, permutation, and so on, they are also differentiable. So in the sense that the computation graph you had in mind is actually dynamic. So at runtime, depending on which branch you choose, and the topology of that computation graph can change from time to time. So in that sense, you can just compose an ordinary, almost you can compose an ordinary NumPy program and apply automatic differentiation through it. And nowadays, with rapid development in deep learning, we had all those fantastic differentiable programming tools. So JAX is the one I used for the demo. And in Julia, people also had quite nice tools to support automatic differentiation. And with all those preparation, I think it's time for us to think about differentiable scientific computing. That was because many of the elementary scientific computations, they are.
Sorry, excuse me.
Yeah, please. Yeah.
I'm curious. Will you comment on differences between these packages, because this is always what.
Yeah.
Curious.
Okay. So if the work you try to achieve was not too heavily rely on deep learning pipelines, I would recommend JAX, because JAX, you can view that as even low level than those PyTorch, TensorFlow, and others, because it's not purposely oriented around deep learning. This is essentially differentiable NumPy with GPU acceleration. So also in JAX, it has nice support for forward mode automatic differentiation and high order automatic differentiations and so on. So in Python world, I would recommend JAX. And those three, they are Julia libraries. And SciML is, I think, built with a strong focus on ordinary differential equations. So if the calculation you had in mind has strong connection to ODEs, so please look at SciML, that's a Julia library. And this is like more specific ones when the calculation is invertible. Yeah, please pay attention to JAX. I think this is also the technique, the library Joseph Kalia is going to teach us, right? Okay, so usually in a machine learning or deep learning libraries, deep learning, I mean, in quite conventional, or let's say old-fashioned neural network, the important elementary calculations, dense matrix modifications, or sparse matrix calculations if you do convolution, and nonlinearities. That's it. But very often, if you focus on scientific computing, you can easily go beyond those two operators, like FFT, eigensolver, SVD. But luckily, those things, they are also differentiable, as we are going to say. Also, ODE integrations, they are also differentiable. So with all those supports, I think now it's time for us to think about, at least in my domain, to talk about like differentiable Monte Carlo tensor networks, molecular dynamics, DFT. So like 2 or 3 years ago, when I first make this slide, I think there was no those things. Differentiable Hedgehog was there, but the differentiable kind of a tensor network was not there. But nowadays, I think you can find papers or discussions along most of those things. So making those conventional or standard computation, physics or computational chemistry method differentiable allow us to solve learning, control, optimization, and inverse problems more freely and more creatively, actually. So for example, the first example I showed to you, this inverse Schrodinger problem. Now let's look at its computation graph. It's actually very simple. It's one-dimensional chain. The starting point is that potential. It's a vector defined in one-dimensional space. So using that, we actually build up a matrix, and then we carry out matrix diagonalization to get the wave function. Then we calculate density difference. So along this one-dimensional chain, there is only one step that is non-trivial: matrix diagonalization. And in the library I was using, JAX, they happen to support backpropagation or differentiation through matrix diagonalization. So that's why automatically you can compose such a program and compute the loss function with respect to the input. That's it. By the way, even though this is a very simple demo example, this can be useful for so-called inverse constraint problem in density functional theory. So inverse constraint means, again, you need to design the potential so the density is what you need. So we can think a bit deeper about differentiable eigensolver. So this case step we used for such a calculation, because it actually has connection to what we already know from quantum mechanics. So again, so this is the step. But I think from this time on, for all these calculations, we should view them as one intermediate step or as a primitive in a long chain of calculation. So here, H, this Hamiltonian or the matrix, is actually an input to this computation step. Then there is a branch. I get, so let's say there's a fan out. So because from this calculation, I get two outcomes. One is my wave function, one is the energy. And then probably I'm going to use those calculations in certain downstream calculation until in the end, I got a scalar valued loss function. And when I talk about differentiation through this long chain of calculation, locally, I just need to care about what's going on for input and output in this local step. So we learned about forward mode automatic differentiation. This was asking the question like, what happens if I perturb my Hamiltonian a little bit? What is going to happen to the outcome? So this is nothing but the perturbation theory we learned from quantum mechanics. So when you look at the equations, they are the same. And we also learned about the reverse mode automatic differentiation. This is asking something, a question that is slightly different. So it's like, in the end, I got a scalar valued loss function R. And then for some reason, I had the ability to propagate this adjoint information all the way to this step to get adjoint for my wave function and energy. How should I do this back propagation for one more step such that I got adjoint information on my Hamiltonian, right? Adjoint information on my Hamiltonian is partial R, partial H. This is the information I need to tune the Hamiltonian. So this is slightly different from what the quantum mechanics perturbation theory, I call this transposed perturbation theory. But the ability to do that actually give us ability to perform Hamiltonian engineering in a very efficient way. So you can think of various applications, right, to design certain Hamiltonian so it has the right band gap or the right physical properties. Actually, people was doing that for model systems or for photonic crystals and so on. So this is a differentiable eigensolver. Yeah, let me skip this for a moment in matter of time. The other thing I mentioned that is differentiable is the ordinary differential equation. So actually those things, they have a nice connection to so-called residual networks, because the residual network is a thing where you do transformation to your input, then add the outcome to the input. That's a so-called residual block. People invented this to let the gradient pass through very deep neural network more easily, because if you initialize those blocks with very small parameters, this is initially this is almost an identity transformation, so it's easy to train. But when you look at those two equations, one is tempted to kind of view this as an Euler's discretization of a continuous time ordinary differential equation. So this gives people something called the neural ordinary differential equations. So basically, you can view those discretized, very deep neural network, a certain kind of approximated discretization of a continuous dynamical systems. So in this way, you can formulate your learning systems directly in the continuous time. So essentially, you are learning a continuous time dynamical systems to achieve its goal. So in that sense, depth is not that a meaningful kind of a way to talk about your systems, because depth translated to some kind of integration step. But for adaptive integration scheme, the number of steps you need to do integration is actually get tuned on the fly during the integration. So what was meaningful is the total amount of integration time. So this is a neural ODE. But the cool thing is to send the gradient information through an ordinary differential equation integration is related again to the so-called sensitivity analysis of ODE and so on, and to backpropagate through an ordinary differential equation. Intuitively, I think you can even imagine that. You just need to integrate another set of ordinary differential equation, but backwards in time. That's it. So I left it here as an exercise, but this allows us to learn not only neural networks, but all kinds of dynamical systems, because you are almost ubiquitous, again, in science and physics, chemistry, right? So here is one example. For example, in physics, a very fundamental guiding principle is the principle of least actions. Basically, you have a Lagrangian and you integrate it to get action. And to solve optics and classical and quantum mechanics, or even field theory, you just need to minimize this action. But again, if you do ds/dt on both sides, you're going to see that the objective function can be regarded as an outcome of certain integration. So in this way, you can actually carry out this class of solver by backpropagating through an ordinary differential equation. So I prepared this example again for my student. So this is related to the rapidest descent problem, that the famous one, I think we all know, right? But suppose Bernoulli didn't solve that problem more than 300 years ago for us. So now we can regard it as a machine learning problem, because here the objective is well defined. It's a total amount of traveling time for these little balls. And the thing we want to learn is a one-dimensional curve with fixed end in the beginning and in the end. So let's imagine we parameterize such a curve with a neural network and so on. Then the objective function involves integration depending on this one-dimensional curve. But nevertheless, we can differentiate into this one-dimensional integration and compute the gradient of the total amount of traveling time with respect to the parameters in this one-dimensional curve. So we can learn that beautiful cycloid curve, I guess, Bernoulli solved for us, but now with a neural network. So that is the code online. So later on, if you click that link, you're going to see the code with neural ODE. So another application domain is the control of dynamical systems. So dynamical systems in quantum and classical domains all has this name, this kind of form. For example, in quantum optimal control, so basically we want to tune certain kind of time-dependent Hamiltonian. So in the end, after certain time, the unitary related to that Hamiltonian is what we need. This is useful for design, for example, quantum gate in quantum computing. So when you go to those quantum optimal control literature, there are actually a large number of methods that people developed. And this is one of the diagram. But now let's view those methods from the lens of automatic differentiation. Then immediately you are going to see that some of those methods are not scalable because they are not using gradient. Because using gradient is the only known way for us that we know to scale up the training for large number of parameters. Okay, so and then there are some methods that was using forward mode automatic differentiation that from this one-dimensional chain graph, we know that it's going to be slow if the number of parameters is huge. And then there are some other classes that is equivalent to reverse mode automatic differentiation. However, very often they make additional assumptions that this control is a piecewise constant, because sometimes this makes the whole thing easy. But from the discussion of neural ODE, we know this is unnecessary. So we just view dynamical control problem as an ODE, integrated from the start to the end, then backpropagate through it. That's it. So in that sense, I think differentiable programming, in particular through neural ODEs, offers a quite unified, flexible, and again, can be more efficient way for performing quantum optimal control. So again, I prepared a notebook for you to explore such a thing. So it's called neural Schrödinger. So this is a standard setup where you have certain drift terms and controllable Hamiltonians, and U of t is a pulse that you can control. Usually people send microwaves to their quantum chip. And you can expand such a control field using Fourier series, and you had certain control parameters. Then like our inverse Schrödinger problem, this is almost end of the story, because once you define that as a kind of a machine learning problem, you have your loss function, right? The fidelity between quantum gates, and you have your computation procedure. So now it's not diagonalization, but ordinary differential equation integration. Again, this is differentiable. That's it. So you can actually get very high fidelity, like 9 zeros, I guess. Sorry, 9 nines in the fidelity, and you can look at the control and so on. And you can inspect the Hessian and so on. So I let you play around with such a notebook later on. Yeah. So I guess let me speak for another 5 to 10 minutes, then we take a break. Yeah. Okay. So another topic. Question? Yeah, please. Yeah.
So I'm sorry, because I didn't quite catch what's the neural thing about this OD. So is it just automatic differentiation developed for neural networks, or I mean, I missed something. I mean, I probably
missed so the neural OD is just it's a name of this paper. So actually, in the Schrödinger equation calculation, there's no neural network, right? So it's just the ordinary differential equation with some parameters expressed as a Fourier series and so on. So there's no neural thing. So, but the name neural OD, as I understood, comes from the connection between residual network and the ordinary differential equation. So you just view them as the same thing. So actually, the way to compute its gradient is also quite similar. There's a unified scheme. So that's a neural.
Okay. Perfect. Thanks a lot.
Yeah. Okay. So finally, to my own work, differentiable programming tensor networks. So tensor networks, they are actually quite useful tools nowadays for quantum many-body systems, statistical mechanics problems, and also machine learning. So, but let's look at really the very basic example of tensor network applied here to the Eigen model. So because remember, for the Eigen model, usually we care about the partition function, phase transition, and so on. And there is a way to solve such a problem with tensor network, because you can express the partition function of Eigen model as a tensor network, actually an infinite one. Then you can contract that gigantic tensor network into one number. This number is the partition function. That's it. And the way to contract the tensor network is called tensor renormalization group. It has this interesting name because sometimes it looks like you do some cross-graining, right? You glue two tensors together, then glue another two tensors together. So you reach thermodynamic limit exponentially fast and so on. But nevertheless, you can view the calculation of tensor renormalization group as a computation graph. So here the starting point is the inverse temperature because that's the only parameter in the Eigen model. And the outcome of such calculation is the free energy log Z. And in each step, you iteratively perform certain calculation to the tensors, you do SVD, you contract them together. But the total number of steps you perform such a calculation from tensor normalization group perspective is the RG step. But from a computation graph perspective, it's basically the depth of that graph. So nothing prevents you to compute first order and second order gradient of log Z with respect to inverse temperature. In this way, you get energy and specific heat. So this is just a tiny demo to show you, indeed, this is possible. And actually, this is a quite brute force way of computing physical observables from tensor calculations. Because otherwise, for specific heat, it can be actually a bit tedious and sometimes even non-trivial to compute those things numerically. And again, I leave an exercise to you because in the original publication, in the paper, we were actually, in this paper, we were actually using PyTorch to compute second order derivative with reverse mode automatic differentiation. That was because in PyTorch there is no forward mode. But nowadays, I think as a simple exercise, you can use JAX or Julia to re-implement this because this is really easy, but it's an entrance level example let you get an idea of different pieces. But this time you can use forward mode. This is going to be more efficient and more memory friendly. So for the same task. So the generalization of the same idea also applies to Eigen spin glass, right? So not infinite, but finite ones, where you can differentiate through tensor network contractions to get optimal configurations from optimal energy. So those are for the classical models. And tensor network finds also an large amount of applications in quantum ground state calculations. That was because you can express a quantum many-body ground state as a one-dimensional or two-dimensional tensor networks. And then what we are facing here is an optimization task. You need to optimize those tensors such that the expected energy is optimized. Conventionally, people usually perform imaginary time evolution, some kind of projection schemes to such a wave function. And very often people saw that the energy was not that low. This immediately brings us some certain question. So we do not know whether this is because we already reached the limit of this given tensor network ansatz with finite number of parameters, or whether this is because we face a bottleneck in the optimization. I guess this is a quite ubiquitous problems when you do optimization for those large amount of calculations, because when the system does not perform well, you do not know whether the bottleneck is in the expressibility or the optimization. But nevertheless, the conventional belief for those tensor network calculations was that this is really because of the limitation of the tensors. So people try very hard to increase the number of parameters in those ansatz so that it gets more lower energy and more correct physical answer. However, if you apply automatic differentiation to the whole systems instead of performing imaginary time evolution, you're going to see that you can still push down energies. Actually, you push those energies further down. So actually, it's very close to the exact answer in this example to the two-dimensional Heisenberg model because it's time-problem free. There's alternative quantum Monte Carlo method. So here I just want to briefly compare this direction with another orthogonal direction related to neural network answers, right? So neural network quantum state, that's using neural networks as answers for the variational wave function and optimize them with variational Monte Carlo. But here, the idea is to use more traditional tensor networks as answers, but bring the differentiable programming techniques from machine learning, optimize them with gradient descent. So use it for the two-dimensional Heisenberg model, you can reach like 10 to the minus 5 accuracy. That was in this plot somewhere here. And also this is the infinite system size. So this actually bring us a lot of hope of push forward those tensor level calculations for more challenging frustrated magnet, fermions, and even thermodynamics and so on. So there are some detailed results, but let me skip in light of time. If you are interested, we can discuss about them. So this is related to the tensor networks. Let me think. I guess let's take a break here, and I can continue after the break. Okay, is that okay?
That's perfect. Does anyone have questions maybe before the break? Anna?
So maybe I have a silly one because I was always curious. So when we go to really basic elements, so like single partial derivative in this all chain rules and stuff, are they numerical derivatives or there is some smarter way of doing that? Because I don't have an idea how, like, what's the something else that numerical derivative, but then I imagine that error will be sorry. So what do you know?
So let me make sure I get the question right. So you mean for elementary calculations, how it was actually implemented, right?
Yes,
yes,
exactly.
Okay, yeah. So if you look closely here, you see it's implemented as an analytical formula. For example, the derivative of exponential is exponential. The derivative of log is 1 over x, and so on. You just put like equations from calculus there into these elementary definitions. Then the whole system glue them together. That's how it was done. Okay,
so maybe I didn't just imagine that you can. That you always can really extract that to this form. But okay, so great, thanks a lot. There is one more question.
Yes, please.
I have just curiosity in the case of the protein folding.
Yes.
What differentiating is this Langevin dynamics. You need to have, let's say, an analytical description of your dynamics to be able to do this. Or I don't know if you can comment a little bit how it.
You mean how is this implemented? You mean is that the question, yes. Right?
So do I need to have like an analytical expression for my Langevin dynamics? In order to
no, actually not. So from a high level, let's say in principle, you can kind of, if you do not care about performance, let's say, you can blindly apply automatic differentiation to those programs, DFT or non-joint dynamics. So it is going to give you a gradient. But very often, this is not the smartest way to do so. Very often people combine the system, automatic differentiation system, with analytical knowledge. So it saves memory, or it's computationally or numerically more stable. Usually it was implemented in this way.
Okay, thanks.
But the analytical derivation was not necessary condition. So again, I try to, let me give you this kind of, because there is, let's say, a very smooth spectrum of a fully automatic differentiation system and fully analytical derivation. So this was also kind of illustrated here in the tensor network example. So this was kind of a gradient expression people derived for certain kind of tensor network calculations. So this is like one end of the spectrum. So the other end of the spectrum is just write this tensor network calculation and give it to the system. So those are two limiting cases. But even between those two, you can find many of the intermediate steps. Actually, in the middle, there is a sweet spot. You do some of the automatic, some of the analytical work. Actually, this is what this is the some of the message I try to convey here. Yeah.
There's another question.
Yeah, please.
It's not a question; it's more a comment on Anna. Basically, a classical processor has only very few operations that it can do, and like very simple gates. And to all of these gates, we know the analytical derivatives. This means that for any given operation, it's just a chain of these, and that means we always can find the analytical derivative.
Right. This is like in the extreme case, you're just building on all this intrinsics, right? Thanks.
Someone else? No? So how long break? 15 minutes. Lei, what do you think?
15. Okay,
Or
15 minutes. Sounds okay. How about let's meet like 15 past. Is that okay?
Yeah, perfect.
15
So
past.
11 minutes. Good. See you
Okay.
in 11 minutes.
Okay, thanks.
Hi, Lei, are you ready?
Yes.
I think we're also ready. So let's continue.
Okay. Yeah, let's continue. So differentiable programming quantum circuit. So as I mentioned in the very beginning, there was actually a hidden connection between graphic models, neural networks, tensor networks, and a quantum circuit. So certainly you can apply those techniques to quantum circuits because actually they are specific instances of tensor networks. They are unitary tensor networks, actually. So the motivation here comes from variational quantum algorithms that I believe you already hear a few times in this school. So let me jump directly into the setup, because to develop certain of those variational quantum algorithms, at least at the moment, we very often carry out simulations of differentiable quantum circuit on classical machine. So this then requires to compute gradient of parameters on a quantum circuit quite efficiently. So certainly you can just like some of the existing solution, just write a quantum circuit simulator using existing machine learning libraries. Then, for example, TensorFlow or PyTorch and so on. Then automatically you are going to be able to differentiate the simulation and get gradient. But like we learned, usually this was done with reverse mode automatic differentiation, because you view this simply as a certain kind of neural network with complex parameters, with complex numbers running through. So the reverse mode automatic differentiation in the simulation can be quite memory consuming. But since you are doing a quantum circuit simulation, memory is already a pressing issue. On the other hand, you can also do forward mode, but this is going to be slow if the number of parameters is too large in the simulation. So actually there is a way out. So to say the way out, let's come back to the computation graph of a quantum circuit. So because what is a quantum circuit? You just have to send some input quantum state. Then you run layer by layer by applying a bunch of unitaries to this quantum state until in the end you get outcome. And on the outcome, you do measurement to get certain objective function. So this graph is the same comp graph as a feed-forward neural network. Remember, in the feed-forward neural network, this is your data, classical data. Those are the weight and the biases that you multiply to the data, right? So topology is the same kind of computation graph. However, for a quantum circuit, it's one specific property. So this is going to be reversible because in each intermediate step, you are applying unitary matrices to the state. So this means that you can actually run this computation graph backwards. So here the word backwards means you run the graph backwards. It's the same backward, but it means differently than computing the gradient backpropagation. So this is actually quite important property because of the reversibility of this quantum circuit. In this way, you can, for example, still carry out reverse mode automatic differentiation, but you do not need to store anything in the forward calculation, because when you do backpropagation at any time, you can just do so-called recompute calculation to get those intermediate state back. So that's it. So certainly this is not something new, because for example, people in classical machine learning knows this trick for reversible neural network. Also, neural ODE is actually doing the same trick, right? When you do backpropagation, they just integrate ordinary differential equation backwards in time. So here you run quantum circuit backwards in time. But this gives you a way to train neural network without store activations or quantum state that is proportional to the number of steps. This allows you to really train, for example, a 10,000 layer, 300K parameters quantum circuit on a laptop using YAO. This is implemented in YAO. And I think nowadays also in TensorFlow Quantum and probably Paninan. I'm not sure, I haven't checked closely. So YAO is a Julia library for carrying out quantum circuit simulation. But from the very beginning, it was designed with the strong focus on differentiable programming. So you can easily compute gradient of those intermediate parameters. The two leading authors are Roger Law and Jingguo Liu. If you are interested, please check them out. So this concludes the first lesson related to differentiable programming. You see, this is a code technique we pick up from deep learning and apply to object that is beyond neural networks, right? Tensor networks and quantum circuit. Okay, now let's move to a second lesson, representation learning. So this is a word you're going to hear very often when you go to machine learning talks and look at machine learning papers. For example, this is a second figure from MIT's deep learning book. So it's showing you when you train a deep neural network for classification. So after training, the low-level neurons pick up edge information, that is the fast change of the pixels, while the high-level high-level neurons, they get more sensitive to object. So it's like the neural networks get a kind of abstraction power by picking up more abstract concept during training. So people call this representation learning. And to really understand and have a productive control of this fact, I think it's one of the most fundamental issues related to deep learning. So that's why it's a second figure on just the 6th page of the book. So for example, here are some usage of learned representation. For example, because the deep neural network separates low-level and high-level features, you can use them to do style transform. You mix the texture information and the content information of two pictures into one picture. So mathematically, I think what is the content and what is the texture of an imaging is not that a well-defined mathematical object, but by making use of the representation, you can already mix them in practice. So the other application I like very much is a latent space interpolation. So for example, by tuning a few variables, they can interpolate between human faces of the pictures of human faces. So imagine how should you carry out such an interpolation in practice. So suppose you just simply add the pixel value of two images together, then divided by 2. So I think very often you will not get a meaningful picture of a human face, okay? So what was done here was that they first train a neural network from the pixel space to certain kind of latent space, where the distribution is simpler. Then they map two images into latent space and perform the interpolation in the latent space. Then while the inverse transformation of that neural network, they map the interpolated latent vector back to the pixel space. So in this way, you do interpolation between human faces. So those are the usage of learned representation, and this naturally brings us a question. So what is representation, and what's a precise mathematical definition, and how can we design a learning system get useful representation and so on? I believe until now, this is still a widely open question. And but there is one fact I observed. So related to how do you get useful representation, there was actually kind of a development in deep learning taking full circle, because like 15 years away, people was using pre-training of so-called deep brief net to get good representation for downstream tasks. But around 2010, people find out, at least for many of the classification tasks, you can completely avoid so-called generative pre-training, simply use all those like techniques or tricks, setting up learnable architecture that is easy to propagate gradient. But nowadays, again, one of the central topic people talk about, for example, GPT-3. But what is GPT? So it actually means generative pre-training. So again, people come back to the old idea of setting up a generative model to do certain kind of pre-training tasks. Pre-training means that irrespective of the downstream, the actual tasks that you are going to solve, you just set up a learning architecture for so-called generative learning, because you hope that to achieve good performance in the generative learning, you get good representation. So what is a generative learning? So I'd like to make this kind of analog. So first of all, we already see many examples of discriminative learning. This is classification and regression. So essentially, you are fitting a function, or you try to learn a conditional probability where X is a data, Y is a label. So the analog was that was like teach a child to read a book, to recognize those characters or recognize those pictures. But the generative learning tries to achieve a different task. It's like teaching a child to write digits or draw a picture. So this requires an understanding or representation of joint probability distribution of data and label or your data, because you had the ability to know all those natural imagings or digits and create a new symbol or new imaging that follows that distribution. So from my daily experience, I had this impression that generative learning is harder, and it requires a deeper level of understanding. So this is the reason why people use generative learning to as a way to get good representation to simplify downstream tasks. So Richard Feynman had this famous quote, "What I cannot create, I do not understand." I think this is true for many branches of science. The ability to create something new indicates the highest level of understanding. So now this sentence actually becomes a slogan for people believing generative learning. There was like a news from 3 years ago. There was this art sold for close to $500,000 US. But if you look at the signature, it was actually a loss function of a generative neural network. So that actually maps Gaussian noise directly to this imaging. And in science, people was also thinking about making use of generative models, the ability to map simple latent attributes from low dimensional space to the physical configurations, like position of atoms, like color of pixels, and so on, in high dimensional space, to generate molecules to help engineering matter, and so on. So to put this more precisely, the task of generative modeling is to express, learn, and sample from a high-dimensional probability distribution. Because when we saw those nature data, we just view them as independent samples from an identical distributed distribution. This is a generating property of a nature that we do not know, but we know samples from it. And a defining feature of those objects is that it's high-dimensional. That was because just thinking about MNIST imagings. So how many possible imagings you can fit into that 28 times 28 space? So it's a gigantic number, right? It's 2 to the, imagine this is a binary, then it is 2 to the 784. So it's a dimensional Hilbert space. However, if you go through those imagings, you are going to see that most of them, they are random imagings, except at the tiny corners, you get meaningful imagings like those. So again, in machine learning, this is a very recognized feature or fact. They know that the imagings encountered in AR applications occupy a negligible proportion of the volume of imaging space. And the goal of a generative model is try to capture this nature manifold of nature data by usually by connecting those data to certain kind of simple latent vector. So you can generate them or sample those data more easily. And those latent space is the representation that we are talking about. Okay, so very naturally, people actually by nowadays already devised different kinds of so-called generative models. Basically, the goal is to capture this high-dimensional probability distribution. But at least to this audience, there is actually an interesting fact. That is, if you look at those models, most of them, I'm not going to talk about them, but you're going to see they have their physics genes. Like you see the word variational, you see the word Boltzmann. Actually, you learn about the Boltzmann machine in this school. And there are actually new kinds of generative models being proposed, like tensor networks, quantum circuit, and so on. So this was actually due to a fundamental connection between the tasks here and the problems in quantum and statistical physics. Because the task of generative modeling is that we are given certain number of samples from an unknown generating distribution. And the task is to model that unknown probability distribution and then generate more samples. Or let's say, by modeling that generating probability, we get certain low dimensional, or let's say disentangled representation of this fact related to those data. That's the tasks of generative modeling. While in statistical physics, usually what we know is an energy function of the Boltzmann distribution. However, given the energy function, usually it's still a non-trivial task to get samples from the energy function, not even to say get the partition function of the energy function, because partition function involves a high-dimensional integration or summation. So you see, statistical physics and the generative modeling, they say like two different sides of the same coin, but the highly developed generative models offers us a chance to solve physics problems because they are good at sampling and representing high-dimensional probability distributions. And in reverse, nowadays, there are also some interesting works trying to design new generative models with physics insight and so on. So in the next like 30 minutes, I guess, I will only focus on one particular class of generative model, that is something called a flow model in this family tree, and trying to discuss how it achieves learning of an useful representation and how it's relevant to physics and chemistry and scientific problems. So for general discussion, you can refer to my note for another school. So this particular example is called Normalizing Flow as a generative model. We already saw one of the applications. This is the OpenAI's Flow model. So Flow model also powers something called WaveNet. That is a speech model produced by DeepMind. By the way, this model was already deployed in Google's product. So those are the real-world applications. But the essence of flow model is actually extremely simple. You can even view or understand it from the limiting case of a neural network with only one neuron. So a neural network with only one neuron is nothing but a nonlinear function, looks like that. But in this limiting case, there is already something interesting happening. So imagine in the input space, I call this latent space, okay? So I had a random variable with Gaussian distribution. Then this one neural network will deform the input into a bimodal distribution in the output. That's called physical space. So by the way, this is actually invertible mapping. So this is the idea of normalizing flow. So because it maps interesting distribution, a normal distribution, or let's say a simple distribution, to a kind of a more informative distribution. This is for only one variable, but you can generalize this to high dimensional space to make uncorrelated variables become correlated. But the mathematical essence is just this change of variable formula. But you do change of variable with a learnable neural network. So as a consequence of this change of variable, you get additional Jacobian term that modifies the distribution in the input space. And because change of variable transformations, they are composable. So you can compose a number of small neural networks into a deep neural network and make the whole thing learnable. So this is the idea of normalizing flow. And the typical usage of normalizing flow is to, if you have a given data set or given physical problem with the energy function that looks like complicated, you try to set up an invertible neural network to perform change of variable to the microscopic variable, such that in the latent space, the distribution becomes simpler. This is the learned representation I was talking about in this part. So this is the basic idea. And for the actual design of those normalizing flow models, there are some basic design principles people try to follow. First of all, is the composibility. As I mentioned, you're going to see that in the actual application is really like combining Legos, because you just define primitives and set up very complicated systems. That's one thing. The other thing is to balance the computational efficiency and the physics inductive biases. So those models, they are invertible transformations where you care about the determinant of the Jacobian, because this determinant is the thing that enters into the probability transformation. However, as you might know, that a determinant computation is n-cube scaling. So very often this is not favorable. So people have thought about a lot of ways of reducing the computational complexity of this term. A simplest idea probably you can have is like to set up the transformation in this like lower triangular form. So this is called autoregressive. This brings a connection to ground class chaos talk with recurrent and autoregressive kind of architecture, there, because the dependence of those variables, the Jacobian is easy to calculate, right? Because for lower triangular matrix, the determinant is you just multiply the things on the diagonal. So the other idea is to impose some of like the block structure in the Jacobian, because for the Jacobian for the determinant of the whole matrix, you just look at each of the individual blocks. So there are some other ideas we are going to see later on, but those are the basic design principles. When you go to literature, I guess first of all, you need to pay attention to those kind of choices. Let me skip this kind of details because this is one example of one particular and also very popular block. It has a funny name, but it's actually very simple. I leave this as a kind of exercise or demo of some of the considerations here. So this is the kind of a mathematical introduction to invertible neural network known as normalizing flow in machine learning. Now let's come back to physics. So how is this kind of setup going to be useful for physics? So again, let's start from a rather simple toy model. Think about the coupled harmonic oscillator, a classical one. So in the, let's say, physical space, the variable we got, that's x1, x2, the coordinate of those two oscillators, and they are coupled. And if you think about their Boltzmann distribution, it's a tilted Gaussian because there is a correlation between them. And if I have an invertible transformation to those variables, a very physical kind of transformation I'd like to do is actually to decouple those two degree of freedoms, right? I'm going to get the relative motion and the central mass, and they are going to be decoupled. If I scale them in a right way, I can map this tilted coupled Gaussian into an isotropic Gaussian. That's a normal distribution. But basically, the thing I had here is a normalizing flow. Actually, it's an extremely trivial normalizing flow that does linear transformation. The transformation is like 1, 1, 1, minus 1, like something like that. But the point of normalizing flow is that it can go beyond this simple setup in two directions. First of all, a neural network can perform nonlinear transformation. Second of all, a neural network acts on all the variables, high-dimensional variables. So it acts on high-dimensional space. So along these two directions, normalizing flow can be useful. And you can imagine that probably I'm going to do a nonlinear, high-dimensional, some kind of normal mode transformation to the input data to get isolated, decoupled, kind of collective degree of freedom. This is something I want to achieve, okay? So naturally, this brings kind of connection to existing topics in physics. For example, renormalization group, where there, the idea is to perform transformations to microscopic variable, and then you get more cross-grained variables, and probably you have fewer of them, which gives you kind of effective description of your original systems. You're going to say this is indeed related to normalizing flow. So the other thing is for practical calculation of statistical and quantum many-body systems, very often we do so-called Monte Carlo simulation. However, if you do that, very often you're going to say that an efficient Monte Carlo update sometimes can be difficult. That was because interesting physics usually lives on a manifold. Like those nature imagings, they also live on a manifold. If you do a simple-minded interpolation or manipulation on the pixel, sometimes you violate this natural constraint, so it's not going to be natural. So here is the same idea. If you violate this manifold constraint, those update is not going to be efficient. So how do you capture those natural manifold of statistical physics system? Actually is a key guidance to design useful Monte Carlo update. So with those considerations, actually, together with my student, we set up certain kind of invertible neural network by composing bijective primitives. So we stack them in this fashion, and after every transformation, we keep carrying out transformations. So to some of them, I call them collective variables, and we stop doing transformation to some of them, I call them latent variables. So overall, this becomes an invertible transformation between collective variables, correlated classical variables, and latent variables. And from X to Z, this is like a cross-graining RG. And since this transformation is invertible, so from Z to X, this is the generative model kind of sampling procedure. And remember that mathematically, such a transformation is actually change of variable. That means we still have this formula related to the probability transformation coming from change of variable. But now I took logarithmic on both sides of the equation. So we know that the logarithmic of probability is nothing but energy. So now I'd like to read this equation differently. So I'd like to view log P as some kind of a bare energy function I have for my classical variable. And while layer by layer training a transformation, I got additional correction to the bare energy, right, from this Jacobian term. So I view this as renormalized energy function for those latent collective variables. So basically, this is a quite literal implementation of invertible transformation, invertible renormalization group transformation using a normalizing flow. So using that, you can train that with variational principle. So basically, the training procedure is equivalent to a variational free energy calculation. So the loss function has a physical meaning of a variational free energy. And after training, like we saw for those image model example, so here, this network maps the original correlated microscopic variable to more disentangled, or let's say uncorrelated collective variable. And for those collective variable, you can do very simple single spin flip update. But those single spin flip update in the latent space would corresponds to non-local collective variable update in the original physical space. So this offers you a way to perform kind of more efficient sampling by pushing samples from latent space to the physical space. So those are the possible applications of normalizing flow if you stack them as a block. By the way, for those of you who knows tensor network, so you might recognize that we are actually borrowing the architecture from tensor networks, right? Actually, we are borrowing the whole thing, the whole setup, except in tensor networks called multi-scale entanglement renormalization group ansatz. Here, each block is a unitary, where those unitary transform entangled qubit to a product state, where in our example, we transform classical correlated variable to a Gaussian variable. So you can view this neural network setup with a normalizing flow as a classical counterpart of this mirror circuit. And another way to view it is for those of you who knows about classical signal processing, there is this quite famous wavelet. Wavelet is a linear transformation to your signal. And like our coupled harmonic oscillator example, you just keep doing cross-graining and only keep this, they call it smooth signal, basically the mean signal, and throw away, or let's say stop doing transformation on the detailed signal. This is their way of calling it. And this neural network renormalizing group setup. Again, generalize this setup from a fixed linear transformation to a learnable adaptive transformation. Learnable nonlinear transformation carried out by a neural network. So in that sense, neural RG is also related to something quite popular and fundamental. So I guess let me let me skip this part because this was related to like pushing the whole idea to the continuous limit. But this is something you can probably check out later. Speaking of the representation, let's look at another example of representation, because up to this point, we were talking about the transformation of classical variables in the coordinate space. But if you think about other class of the transformation we learned in physics, there is actually quite a famous transformation called the canonical transformation. But canonical transformation happens not in the configuration space, but in the so-called phase space, right? Remember, phase space contains coordinate and momentum, okay, P and Q. And to the phase space, there is an intrinsic constraint, or let's say the structure. The structure is called a symplectic structure. That was because to define Hamiltonian dynamics, there is a intrinsic symmetry between, for example, the Newton's equation for momentum and coordinate. And turns out this is related to the so-called symplectic structure, okay? So what does that really mean? It means that very often when we talk about canonical transformation, we actually mean change of variable, because we mean change of variable from the original coordinate and momentum to some transformed coordinate and momentum. But in this case, we need to pay attention to an additional constraint. That constraint is the symplectic constraint, which means that the Jacobian of such a transformation, of such a change of variable, should be orthogonal to the symplectic matrix. So this is also called symplectic constraint condition. So why we need to pay attention to that condition? That was because only for those class of symplectic change of variable, after the transformation, we can still talk about Hamiltonian dynamics. So in the transformed phase space, we can still talk about the Hamiltonian equation motion, where they follows its own Hamiltonian evolution, where with a transformed Hamiltonian and so on. So this symplectic condition makes sure that the change of variable has a physical meaning. So this is canonical transformation. Very often people make use of canonical transformation to, for example, simplify and solve Hamiltonian systems, because if you find the right transformation, probably you can separate variables where each z has an independent motion. So actually, this is an example where Charles de Nolay, who spent more than 20 years of his life trying to find out canonical transformation that help him solve more than three-body problems. He produced more than 1,800 pages of notes like this. It's because he was trying to analytically derive the canonical transformations to solve these three-body problems. So very naturally, when you look at this kind of effort, there is a question that, is it possible for us to find out useful canonical transformations that is applicable to many-body systems? So with normalizing flow, that is actually possible, right? Because normalizing flow is a class of learnable nonlinear change of variable that is ready for us. And this gives us actually the setup of neural canonical transformations. So essentially, the idea is to set up symplectic neural network that maps small p, small q, that are the physical variables in the original space with complex Hamiltonian dynamics, to a latent phase space variable with capital P and capital Q. And the idea is that the hope is that after the transformation, I can simplify the original dynamics to a coupled harmonic oscillator. Why a coupled harmonic oscillator? That was because that was the simplest example of dynamical systems. That's reason one. The reason two is that the canonical probability distribution associated with coupled harmonic with independent harmonic oscillator is actually a Gaussian distribution. So this is, in that sense, again, it's a normalizing flow transformation, but act on the phase space. So now we only have like one question, one kind of what task that we need to address. That is how to set up a neural network that is symplectic. Remember that symplecticity means that the Jacobian of such a transformation should be orthogonal with respect to that two-n-dimensional matrix. So an ordinary invertible transformation will not satisfy such a constraint. So this is where you combine machine learning tasks, machine learning models with physics, inductive bias, and physics knowledge. Basically, you want to inject physical constraints into the learnable architecture. So again, the answer to this question is we should look for those constructions from our textbook, because in the classical mechanics, we already learned actually so many of the classical canonical transformations. For example, we can carry out transformations, because symplectic transformation, linear symplectic transformation is a Lie group. So we can design the Lie algebra. That's one way. So the other way is that probably we still remember the fact that an arbitrary Hamiltonian evolution is actually a canonical transformation. This means you can set up an arbitrary Hamiltonian. Hamiltonian is a scalar valued function, right? You can set up a scalar valued neural network as a Hamiltonian, and then use that Hamiltonian to drive a piece of time evolution. And this piece of time evolution can act as a transformation to your system. So this is the idea. And this actually also nicely connects to the idea of a neural ODE, except here you need to use a symplectic integrator in your neural ODE, right? The ODE is not, it's actually a Hamiltonian system. You should respect the simplicity. So in the remaining, just I won't run over too much. I just show you one example of this example. So you can, for example, get, molecular dynamics data, where this is the dipeptide. It's a very simple molecule. You get 200 nanoseconds of data. So basically the molecule jiggling around like that. But if you view each snapshot as a sample from a distribution, you can map, you can send those data to a symplectic neural network. And that lets this neural network to kind of separate out independent nonlinear modes of this molecule. And you can read out those modes by its frequency and pick out this low energy, or let's say slow modes. And you are going to see that even though this molecule probably had a 30 degree of freedoms, because there are 10 atoms and in 3-dimensional, but the slowest modes corresponds to, not surprisingly, some global torsion of this molecule around its backbone. This is one example. By the way, this is actually a standard example of unsupervised dimensional reduction. But here, it's a reduction to the space with slow collective variables. And to automatically...
Sorry, a question.
Yeah, please.
Right. So, but like, wouldn't that be a problem that should be easy to solve with just like classical linear algebra techniques and stuff? I mean, just like you know, from the first side, it's like it looks like a problem where why one wouldn't need like some fancy machine learning techniques.
So you mean PCA kind of techniques, right? Principal component analysis. What do you mean by classical linear algebra?
I don't know, maybe just, you know, extracting the frequencies out and then computing the main oscillationary modes, you know, just from like eigenvectors of the of some matrix.
You see, here is the thing. Because there was a hidden kind of other slides to set up this up, so then it should be a quite a clear effect. But nevertheless, the thing was that here the slow modes, they are the kind of global, not global, let's say torsion angles on the backbone of this molecule, phi and psi. And the microscopic variables, they are the Euclidean space coordinate of those atoms. So that means the collective mode in that sense, phi, okay, is a nonlinear function of Euclidean space coordinate. So this wouldn't be a simple normal mode transformation. So if I had a like one-dimensional quadratic chain, like the example I showed there, you can simply set up a dynamical matrix, diagonalize it, you directly reproduce normal modes. But here, you need to do a nonlinear transformation to find the collective variable, collective coordinate. So then this linear algebra, right? Linear algebra has a word linear that. So indeed, it is actually possible to construct a certain kind of a matrix, but this wouldn't be the matrix in the original space. It's already in a different space, like kernel space or something. I hope this is clear now.
Yeah, okay.
Okay, yeah.
We're almost over with the time, so maybe five more minutes. Is this okay for you?
Sure. Actually, this is my plan to end here. So let me bring to your attention some other concurrent works related to this paper. You see the keywords Hamiltonian, symplectic all over the place. So actually, that was quite attractive direction to combine dynamical systems and physical knowledge and neural networks together and so on. So there are other applications related to flow, but let me just skip it. Yes. Let me jump to the end. So that's it. I share with you two lessons. Actually, they're nicely summarized by this, the title of this paper, this classical paper, the learning representations with backpropagation of errors, right? Differential programming, learning representations. And hope those are useful to you. So thank you. Yes, that's it.
Thank you very much. Questions? Are there any more? There were already a lot of questions so far.
Hi, so I have a question regarding automatic differentiation.
Yes.
You've been illustrating it to solve certain optimizations, and I was wondering how it applies to constraint optimization problems, or whether you've tried it out, or well, I don't know. Like what?
So what do you mean by constraint optimization? I mean,
say you have a minimization problem or maximization subject to certain constraints that your variables must fulfill. Like,
okay.
Yeah.
So there are actually applications of that. So one example of it was, for example, some kind of implicit theorem. Like I had a slide for those things. Probably later on you can check those links. So it's more like the optimization was embedded with a fixed point solver. It's like you need to solve certain equation to get its answer, but this answer depending on certain parameters. And those kind of setup plays nicely with the automatic differentiation framework, because sometimes you can regard the solving of that constraint problems as a primitive. Basically, it means you don't care about how you solve that constraint problems. You can use kind of a whatever solver. But once you satisfy a certain condition, you derive again the backpropagation rule through the solver, and so on. A concrete example, I think, would be in those tutorial material and other related references. Yeah.
Okay, thank you very much. I'll have a look at these.
Yeah.
Any more questions? Okay, then let's thank Lei Wang again. Thank you very
Okay,
much.
thank you very much. So
Pleasure to have you here.
yes, thank you. So enjoy the rest of the school.
Thank you very much.
Bye. Yeah,
Have a good
bye.
day.
Bye.